From A section, it's 62, ma'am.
Okay. Note down the attendance, no? Okay. B section, two sections. Uh, no, independently, like section A, section B, Kartikeya and Hemant, individually you take the attendance. Just note down the numbers, that's all. One second. Maybe a net issue is there. Anyhow, if in between there is a disconnection, please patiently wait. I'll connect once again. Okay, in between the sessions also. Okay, screen is visible now.
Yes, ma'am.
Yeah, we'll start. So multiplication, will start with multiplication and go for division also. So that is different. So floating point multiplication. So what are the rules or what are the steps involved is something like we can categorize that into finding the sign bit of the product, that means the result. Then second one will be the calculation of what you say exponent of the result. Next, third one is finding the mantissa. So this 3 we have to take something like for multiplication and division, a minor change will be there. Okay, we'll find what are those things. So to find the product of the result, like for multiplication, if you are taking, say if the both multipliers, say m1 and m2, I'm saying I'm multiplying m1 with m2. Say if they are of same sign, that means either both positive or both negative sort of thing, the result will be positive, na? The result will be positive. Okay, like if any one of m1 or m2 is negative, then result will be negative. Okay, that sign bit thing I'm telling. So this is your first calculation. So what is the operator that can best give us this result is an XOR operation. We need to do the XOR operation, and we can get the value of this sign bit, either 0 or 1. Okay, done. So something like both positive means 0 over 0 and both negative means 1 over 1. It will be positive. That means sign bit will be 0. So this is negative means any other number is 0 sign bit. XOR operation, if you are taking, it will be 1. So it is negative. So this is the identification we have to perform on the sign bit. So exponent bit is something like when you are performing the multiplication, the resultant exponent of the product of the what you say multiplier and the multiplicand has to be found. So this is your first one. Second one is if both m1 and m2, that means the exponents, I'm speaking about exponents now, are biased. What is this biasing? Biasing means x is 3, same biasing. Okay, we can add both the exponents, add both the exponents. Now here, what is this biasing in your IEEE format? What is the biasing we were having? X is 127. Na? This is the bias. Yesterday we have seen what is that bias means. Biasing is X is 127 for your IEEE representation of 1.m representation format. Okay, now when you are taking the multiplication, the resultant exponent of the product will be the sum of exponents. If you are saying, say, exponent of m1 and exponent of m2 is there, say, we will be adding these two to get the resultant exponent. So this will be m1 plus m2 sort of thing. So if you are doing the operation of adding the exponents, okay, and already it is biased. Every value we are taking, say single representation, if you are taking m1 and m2 separately, they are already biased. So what happens is when you are adding these two, we say that the resultant is double biased. Okay, now there needs a correction to be done for removing that double biasing. So subtract 127 from the resultant exponent value what you are getting. Understood this one? Two exponents will be adding for the result. Okay, because this is already in your biasing format, when you are adding it will be double bias. So you have to remove one set of 127, the biasing value, so that you will be getting the resultant exponent. Okay, so and again here we have to see whether there is an underflow or overflow of the exponent. Okay, that means the result, if the maximum result, if it is crossing, what is the maximum result or maximum value we can represent in this exponent 127? 128 now, or you have 8 bits now. So this is the maximum value you can have. If this exceeds, then we say it is overflow. Like after doing the addition of the exponents, if you are subtracting 127, still your value is more than that one, this all values of ones, then we say that it is overflow. Okay. If it is the negative value, minus 127 is the minimum value what you will be having. Now, if this is the value like less than this, if it is there, it is underflow. So you have to find that underflow or overflow of the exponent, and accordingly we need to adjust the what you say mantism. Okay, like how do you adjust that? Yesterday we have seen something is exceeding the limit. Say a number, your mantissa into 2 power say 128 you are getting, say. Okay, it is exceeding the limit, say, or 129 it is there. Okay, how many bits we need to do the operation to be shifted? Say if you are having 1101 sort of thing, one value. Okay, when you take this, I can divide this into say 127 or 128 is the maximum if you are saying. Say I need to set this as 127 2 power 2. That means here 2 shifts you have to do. Decrease this value, you need to do left shift operation. Okay, so that sort of adjustment is needed. So the exponent will be obtained after doing this underflow or overflow calculation. So the last one is your mantissa of the product. Finding the mantissa of the product. Okay, like you can say that this is significant of resultant product because you are multiplying say 2 values of m1 into m2 sort of thing. So it is a normal multiplication we try to do. A normal multiplication is you can use your Booth's algorithm, any sort of standard multiplication you can take. I think you can use this also, no? Shift and add multiplication also. Like when you are doing this iteration of the product of the exponent, like there is no need for the both the exponents to be similar or same value, we'll say. Like this m1 value is not necessary that it should be equal to m2. Why? Because here this is addition of the 2 values we are taking. Okay, for your multiplication the exponents are getting added, so there is no need for adjusting this m1 and m2 to be of same value. You can have any value, that means you can have unequal values, okay, or you can have positive or negative values also, anything. Like what we try to see is the double biased segment will be adjusted by subtracting 127. What is the value you get is the resultant exponent you are getting there. But mantissa thing, if you take, okay, here mantissa for both your multiplier and multiplicand, say you will be taking that in a true form, okay, and using any shift and add multiplication or any Booth's algorithm sort of thing, whichever is you have a code for that or you understood well, you can use that, because this is a standard normal what you say this bits we are taking, and you are having the multiplication process same as it is for a normal multiplier. Okay, when you are doing so, what is the point that you have to remember in the iteration is you are representing this in 1.m format. Na? So is this a value which is shown in your mantissa portion or your fraction portion? No, no. In this mantissa or fraction portion, is this one coming into picture? This one fellow is hidden. This is hidden. Only what you represent is this fraction. Yes or no? Say 1.1101 is there. this value won't be seen here. Only 1101 along with the other bits will be filled with 0 will be represented there. Okay, that means that this is hidden. So you have to take care of the hidden bit value also when you are performing the iteration of shift and add multiplication. Okay, any multiplication process you take, hidden bit also has to be considered into the process. Okay, like after getting the product, after getting the result, taking care of the hidden thing, you have to see that whether the result is normalized or not. What is this normalization? What is this normalization? You are representing that in 1.m format. That means this LSB bit, this fellow should be 1. Okay, when you are not having that value, like after you multiply, if the product is not following this, say if you are getting say 1.10, some result I'm saying, say this is your result you are getting, then this is a normalized form. You are getting 1.m, m is this value. Okay, normalized. Say if I'm having this result, something like this, into 2 power the exponent I'm getting. What should I do? I need to do a shifting operation. That means one bit should be shifted towards right. When you are moving this towards right, whether you increment or decrement, you have to see. Whether you have to increment or decrement, you have to see. Okay, so something like this. Now when you are supposed to put this in 1.m format, this will be 0 1 0 1 1 is the result. Okay, and this will be incremented 2 power e if you are taking. So this will be e plus 1 if you take this out. Yes or no? Now, say if your product after you multiply is of this sort, you are getting, say, into 2 power exponent. It is not in 1.m format. So what you have to do? You have to do left shift operation. Left shift means 1.0101 will be your left shifted value. Now what will be your exponent? It will be decremented or incremented? -1, decrement. You have to do decrement. You have shifted now. Okay, so this is an adjustment that is needed. So when your mantissa portion, like it is not in the normalized form as 1.m format, either you have to shift the product towards left or right. Accordingly, your LSB bit, this is your LSB bit, has to be 1, adjusted as 1, and the correction into your exponent has to be done, either incrementing or decrementing the value. Okay. Again, is this exponent when you are doing so, say already if your E is 127, say, if it is going more than 1 bit added or 2 bits added, that means you are shifting towards right, left. It will be getting added. No? Now this gives a condition of overflow. Okay, the more the value you are trying to shift towards your left, the more the exponent value will be increasing, and it results in overflow of the exponent. That has to be taken care of. Okay, something like physically, if we are taking, we try to use an indicator saying an overflow happened or an underflow happened. A flag can be raised. You can take a flag and indicate that as a result. Now see, I'm taking this now. An example is needed or not? Do you need an example? People are there.
Yes, ma'am.
Say, okay. say I'm taking, say, x some value, say minus 1.5 into 2 power, say I'm directly writing the e value, say 7 minus 127. That means a representation accordingly we will be giving now this e value, what is the value you are representing in your M.1 format, IEEE format. Say I'm taking the same value but positive, say into 2 power, say I'll take one positive value. This results in a positive number, this results in negative number. Okay, exponent will be negative here, this will be positive. As that example I would like to take. Okay, now when you take the sign bit, okay, your sign bit of this fellow will be 1 and the sign bit of this y will be 0. Done. So what will be your complete exponent? If you take the exponent of x is 7, exponent of x is 7 and y is 224. Okay, now when you take the addition of this exponents, what will be the resultant? Should be 231. Na? Your e value is 231. Okay, when you are representing this in your IEEE format, if you take, I'm taking this, say for x, this is 1 followed with 3, 4, 5, 1, 2, 3, 7. Next for y, it is 0 followed with, this is 224 means 1, 2, 4, 8, 16, 32, 64. So this will be 224 if you verify the value. Okay. Now this is 1.m format. 1.5 is equal to, in 1.m format, m is equal to 0.5. Na? So what is the hidden thing? This is hidden value. And 1 followed with all zeros will be 0.5. So this is 1.5. A simple representation I am taking. Okay, this is your 23 bit and this is your 8 and this is your 32 bit format. Okay, now when you are taking these values and adding, okay, what is your resultant is 231. Now this is double biased. What is that we have to do? We have to subtract 127 from this. 127, if you take it out, this will be 104. Is it correct? Yeah. So this is your resultant exponent. Resultant exponent. So the exponent will be, now for the result, after doing the correction of this, the resultant will be, the exponent is 104 it should be. So 1, 2, 4. So 8 is 1, 1, 1, 0. So this is 104 if you check it out. 8 plus 32 plus 64. Okay, 104. So now the sign bit of the resultant, one is positive, one is negative. So it should be 1. Okay. Now mantissa, if you take, your mantissa is 0.5, m is 0.5 and the complete value what we are taking is 1.5. Okay, so 1.5 means this is representation here in your binary format is 1.1 followed with zeros and 1.1 followed with the other zeros. Okay, here hidden we are taking. So if you take this two mantissas multiplied, m1 multiplied with m2, what is the value you get? Now a simplest form is 1.1 into 1.1 if you take, you'll be getting that as 1 over 1, 1 over 1, So 0, sorry, 8, 1, 0, 1. Na? Now you will be taking the decimal point here. Now this is your result. Now is this in 1.m format? No, no. This is 1 point, like completely if you take, this is 10.01 into 2 power 104 it is. And this is negative minus. This is the value you are getting. But this is not normalized. Is this normalized? We need to have 1 point format. So what we have to do a right shift. 1 bit right shift if you do 1.001. Okay. And here doing so, it is to be added. If you are taking that 1 bit towards right shift, you are supposed to add 1 bit. So 1 means it should be 105. Now is this within the limit? There is no underflow or overflow sort of thing. So completely what is the result you get here is this bit will be added, or what you say, this will be 1 now. This is 105. Okay. And this will be 0, 0, 1. 0, 0, 1. This is your result. Now what is the hidden parameter is 1. Done. Is this correct? What is the result we have to get? 1.5 into 1.5. It should be? What should be the result? Are we getting that? This is 2 power 0 plus of 1 by, it will be 1 by
1 by 8.
1 by 8. So that value is correct now. Okay. So we will be able to get the adjustment done, and based on that adjustment we are able to find the complete result. So what is this underflow or overflow sort of thing we are saying? So if you are taking the representation of the 8 bit, complete all ones, if you are taking, that is the maximum value you can accommodate the exponent here, and completely 0 if you are taking, that gives you a negative value. So within that limit, if your exponent is, then it is something like the limitation of minus 127 to 128 sort of thing. If this is within this limit, then this is completely what you say, within the limit. Less than this or greater than this indicates that this is underflow and this is overflow. So if that things happen, we need to do this adjustment, left shift or right shift. How many values we have to shift is decided by how many bits they are underflow or overflow. Okay. Flowchart is needed. Shall I give a flowchart form, or you understood this? The steps. Do you need a flowchart, or let me write that? I'll write it. Okay, let me take this. Now say, what is the first step is, add the biased. Now we start with finding out the exponent. Okay, add the biased exponents of two values or two numbers you are multiplying. Okay, and minus 127 from the sum of exponents. That means here we are making the double bias into a single bias. Okay. This is double bias converted to single bias if you are doing this step. Okay, first you are adding the biased exponents and subtracting. Next is multiply your second step. This significance. Next one is normalize the product if necessary. Where do you see this necessity is something like underflow, overflow sort of thing, if it is there. Okay, um, something like shifting towards right means increment the exponent is an example, or shifting towards left means decrement the, sorry, it's not clear, left decrement the exponent. This is the next step. Okay, next one, check for the overflow or underflow. Okay, something like overflow or underflow. If you check, so if it is S means we go for indication. Okay, something like in our hardware we go for indication or what you say, exception. Next, if it is not any overflow, okay, what is that we have to do is round the significant to the number of appropriate bits. Means what? We are making that into 1.m mantissa format. Okay, that means you will be shifting the bits towards left or right. Okay, uh, when you are finding that element, now if this step is normalization, this is normalization step. Okay, after that still like do one iteration of left shift or right shift according to the need. Now if it is still not normalized, still it's unnormalized form. If it is yes, what have to do? Go back to the normalization. That means this step. Come back here. Again repeat this process. Okay. If it is yes, it is now normalized. Then what is that? We didn't set the sign bit. Set the sign bit, because sign bit last step you can do. Okay, last step you can assign the sign bit. Sign bit as 0 if both positives or negatives, else 1 if positive number is multiplied with the negative number. That's all. So this is your flow, simple flow you can say. And this is for multiplication. Now, what is that we expect for division now? Division step, can I put that in the same flow sort of thing? Yeah. Ah, this overflow is it means like here we try to give an indication of in the hardware underflow or overflow flag will be given. Okay. So if there is an overflow, it indicates that like we need a normalization. Yes or no? Yeah, that this aspect depends upon what is the flag it is getting initialized. Then we check is it normalized or not. So both the things we have to check it in parallel. Something like when you are checking for the normalization of the result, this format you should not deviate. Okay, and the point is that your exponent should not deviate that range of values, because more than the value of all ones, all ones in your 8 bits, it cannot accommodate any one extra bit na, or any extra one more exponent there, and it cannot represent any value below this. Both the things are our exceptions. Like if something is exceeding this, greater than this or less than this, we need a normalization. Normalization means we move the bit towards left or right so that exponent value can be, here it can be decreased, here it can be increased. If something is more than this all one value, what is that we expect while doing the underflow or overflow adjustment? Overflow means you have to decrease the exponent. One value you have to decrease. If an underflow is there, maybe you have to increase the exponent. So if I want to decrease the exponent means a value something here, what is there, say I'm taking decimal point here, I should be getting 1 point something aspect. If I want to take this to decrement the exponent, what is that I have to do? I should be moving this towards, which side? Left side or right side? Here we are mentioning, na, I want to decrease towards your left. If you are taking, you can decrease the exponent. Yes or no? That means it takes care of the overflow. If you are having a value which is less than that minus 127, then you have to increase the what you say exponent. For that, what you have to do the right shift. That means exponent will be increased. Now after doing this underflow or overflow sort of thing, still you are not getting a normalized formula. Like you are not getting this 1 point m. Again there should be an adjustment done there. Both the things we have to do parallelly. We have to see parallelly. That's why we are saying, and this condition is indicated, what to be done has to be decided by how many times that has to be left shifted or right shifted will be assessed. Doing so, is this normalized? We have to see. Is this normalized? Normalized means one point time format you are getting or not. If not, again you have to redo the values there, or redo the what you say positioning of the values. Okay. Yeah. So the other aspect of our floating point is division. So what is that we expect as uh, a difference in multiplication and division is, say for like multiplication, when you are doing the exponent part, say I'm taking the sign bit, say first one sign bit, deciding the sign bit I'm taking. Now both positives, if you divide, what will be your result? Positive only. Both negatives, if you divide, your result will be
Positive.
positive. Done. So a positive with negative or negative with positive, if you are taking, then your result will be negative. So again here we can take XOR operation. Again this also, deciding the sign bit, need to perform an XOR operation on the sign bits. We will be getting the needed resultant value of the sign bit. Done. Second thing, when you are doing the exponent portion. Okay. Now division means it is subtraction. Okay. When you are dividing, exponents has to be subtracted. Therefore, multiplication we added the exponents. Okay, so when this m1, say I'm taking m1 and m2 as two numbers, and their exponents are biased. Say I'm taking biased exponents. When we are taking the biased exponents of both the divider and dividend, okay, both the divider and dividend sort of thing, like if you are subtracting these two fellows, the result will be not having any bias. We are removing the bias. So what we have to do, these biased exponents after subtracting, we need to add 127. What is that? That is the one difference we are having. The resultant exponent. Okay, when you are subtracting e power m1 minus m2 sort of thing I am taking, what you have to do is to this result you have to add 127. That means when you are subtracting, the bias is taken out. That is the meaning. So we have to restore back this bias. So the 127 will be added. Okay, and after adding that, whether this will be an overflow sort of thing has to be checked, because we are adding something there. Okay, what is the check we have to do is overflow. For your multiplication, what is the check that can be needed is something like underflow sort of thing, or overflow or underflow, both the things has to be checked parallelly. Okay, it depends on what the values you are taking here now. Now, here if there is an overflow when you are adding, we need to do the adjustment of the mantissa there, because that cannot be exceeding the limit of your range of 8-bit 1 representations. No? So, the exponent will be obtained by adding 127 to the difference of the exponent values. That. So, that gives you the exponent thing. Now, mantissa portion is a normal division aspect you can take. What is the approach we have seen for a division? Different approaches we have taken. Say restoring, non-restoring also you can use on to the mantissas. Now, these mantissas again will be in which format? 1.m format only. Now, this portion you will be taking. The mantissa of the two values will be taken, and by usual method of division, either a normal what you say restoring or non-restoring format of division you can implement, and you can take the result and see whether the result is normalized. Okay, perform this normal restoring or non-restoring division, anything is okay. After that, you find the quotient and the remainder sort of thing in your set. You now check this result. If this is your result you are getting, you check whether there is any sort of, or what you say, normalization needed. Normalization means again we are supposed to put this back into 1.m format. Okay, so let me take an example with same 1.5. I'll take, let me make my job simple. Say I'm taking 1.5 into, let me take a positive number, say 227 minus 127 is there. Say this is biased number, and I'm taking negative 1 minus 1.5 into 2 power, say 107 minus 127. So what is the exponent we are getting? What is the resultant? What we are saying now, this sign bit we leave it for a moment. Now see, what is the resultant exponent we get? 227, okay, minus of 107 we are doing. Yes or no? What is the result now? 120. Now this is taking out the bias. Now this is cancelling the bias. Now we are subtracting, means both the biases of these exponents are getting cancelled. Means that we need to add 127 for this, we are saying, as per the rule. So if it is 127, 247 is your expected, or what you say, the exponent of the resultant value. Now, so the resultant exponent, now sign bit is, now you are taking positive with negative divided. Now this will be 1 now. And what will be your this thing? 247 means 1, 2, 4. I think 4 1, huh? 1, 2, 3, 4, 1, 2, 3, 4. So this is 147. 147 plus 8. Is this correct? Check the exponent. 247. No answer. 8 bit we are taking. Sign bit. Now natural 1 by 1.1 by 1 means what I need to get is 1 division. Now for this maybe you can remove this mantissa portion, and if you see, this is the value you'll be getting. Decimal point, if you remove and do the division, or with the decimal point you want to take, you can take. Normally you can remove this what is the resultant value if you take a normal decimal division. If you want to take, what is the value? Is this 2.5 or 1.5? 2.5 or 1.5? No answer. 2 power 0 and 2 power minus 1. So this is 1 plus of 0.5. This is 1.5. That is the value we have taken. Here, this one. This is the value. So this 1.5 over 1.5 is 1. So your result should be is this normalized first of all? Is this normalized? 1 followed with all zeros it will be. If I take this value as, let's say, this is in 1.m representation format, my mantissa portion will be all 0, continued for 23 bits. Yes or no? What is the difference we are having from the multiplication and the division? No answer.
We are subtracting the exponents
And
and
adding the bars.
add the bias.
Yes, that is the only difference you have from multiplication. There, adding the exponents, and to remove the double bias, we are subtracting the 127. Here, we are subtracting means the bias is nullified, so add 127. That is the only difference we are having. The other steps will be same. Something like, say, if you we take a flowchart sort of thing, subtract the exponents, okay, and add 127 to a result of what you say, subtracted exponents. Okay, this is our first step in our next. Divide the significance, something like using any standard format. Standard format, divide the significance. Significance means complete value. Okay, that is not a new term for us. Now, we need to normalize the result. Okay, next, we have to check whether there is an overflow or underflow. Okay, so if there is overflow or underflow, just if it is S, we need to do something like we need to go for evaluation of this step by adjusting the what you say your mantissa and the exponent portion separately. Okay, now if it is not having, like it is within the limits of your exponents, now round the round up the significant to what level? 1.m format. Now, after rounding up, if okay, let me take this as judgment only. Normalized or unnormalized, we have to see. Is your result normalized? If it is false, not normalized means go back, sorry, go back and do the normalization of the result. Left shift, right shift element. Okay. If it is normalized, true, then set sign bit doing XOR of both sign values. Done. This is as simple as this now. Okay. So this is all about your multiplication and division. Now coming to addition. Addition, what is the difference? Again, when you are adding a number, say point, sorry, so I am taking 1.5, same number I am taking, into 2 power 2 is there, and say 1.25 into 2 power 4 is there, say. Can I want to do addition of these two, add these numbers. Or like this is floating point addition format we want to perform. Now here in your multiplication or division, we didn't put any like condition of the exponent values. Whatever the value you are getting, whatever the value you are getting in your exponent, directly we add it or subtract it. If it is multiplier, we add it, and if it is division, we subtract it. Done. So division, we subtract it. But here, when you are taking this addition process or subtraction process, we need to have the similar value of these exponents. So doing so, we need to either shift these bits towards right or left. Say something when we are doing so, what is that we have to see is, are we losing any information or are we retaining the information doing the process of this shifting. Say I'm taking a value, say 1.2345 and 1. Say 1, say if I'm taking, say this is -2 and this is +2, what is the difference between, what is the difference between these two exponents now? 4, na? That means you have to do 4 right shifts or 4 left shifts to make both positive or both negative. Am I correct? Yes or no? Yes or no? No answer. I want to do a value to be shifted towards left or right, I am saying. Say general element, say 1.23, same thing 4, 5 into, say your decimal format itself, we try to take to understand this one. I put this in decimal format. Base is this, sorry. Now see, if I want to make this fellow to be positive, what I have to do? make this fellow to be positive? Hmm. I, I want to make this to be plus 2. What should be done? So if I do this right shift or left shift. Now see, if I do this as one right shift, because why I'm taking 4 means, say this is my 5-bit storage space. I cannot have extra another bit to be stored. I will be discarding this one if I'm doing right shift. Now what will be my exponent?
10 power minus 1.
Minus 1.
1.
Now one more right shift I do, 10 power
0.
0. One more, it is 1. One more, it is 2. Now I'll be making these two fellows ready for addition or subtraction. Okay, because it is just directly when you are adding these two, what will be the value? It is 10 power 2 into what is the addition you do this onto your the mantissa and fraction portion sort of thing. You'll be getting the result. Okay, but doing so, what we have to see here is, are we retaining the information? Are we retaining the information? See, much of the information is lost. Why I'm taking this as say like a limitation is, if the storage space is limited, that means we have fixed bits of values. If that space is limited, we may not be in a position to lose the information by doing a shifting operation. That means these are our MSB bits that are going to be lost. The information is going to be lost. Now instead, if I make this fellow to be, see this one I am trying to move. Okay, say if I move this information, say I move one bit towards, what is that I'll be getting? 10 power 10 power hmm 1 na. If I move one more bit towards left, it is 3600. 10 power
0.
0 0, and this is 1123.6 followed with 0. This is 10 power 1 and so on. That means, see, when you are moving towards your left side, you are retaining that MSB information. This information is of importance for us now. See, when you lose this information, when you are losing like this information, if you are trying to retain, the majority contribution is going to be added to the magnitude. If you are skipping towards your left or right, sorry, you are losing the information. That means the precision is going out. Yes or no? The precision of the value is moving out, or it is losing the intact information that is contributing to the result. So you have to be cautious while doing this normalization of the exponents. Okay, you have to do the either right shift or left shift in order to make these two fellows to be equal. You have to do the corresponding right shift or left shift, but doing so you have to make sure that majority of the information is retained. Majority of the information is retained. So you have to decide which side your shift has to be done. The normalization, in the process of normalizing these exponents. So what can be the steps here? Are we expecting much huge complex steps? It's not so complex to like in your multiplication or division you take. whatever the steps I said now. Say sign bit anyhow when you are adding two positive numbers and two negative numbers, what will be the sign bit? Say two positive numbers you are adding, it will be positive, and two negative numbers you are adding, it will be negative. One positive with one negative decides on what? One positive with one negative. No answer. No answer. It depends on what you have the that what you say end around carry coming over. You remember your sign magnitude additions or two's complement addition or one's complement addition. You had something like adding your including the sign bit. Say if you take sign magnitude addition, we add magnitude, then assign the sign bit as the sign bit of your two numbers. Na? I'm not getting answered. I don't think people are there online, hearing or not. Okay, let me give the steps now. So first is for your addition, floating point addition, compare the exponents now. Compare the exponents. If they are not equal, what to be done? You have to, not equal means, uh, yeah, 10, 15. Okay, okay, I'll wind up. Okay then, I'll stop and continue the next hour. So shift left or right, okay, and adjust the exponent accordingly. Okay, I'll continue this in the next hour, okay.